What is Heisenberg's uncertainty principle about? A limit in interactions. B, the influence of a measure on the following conjugated measurement. C, a restriction in simultaneous measurement of conjugated. D, a limit in knowledge of conjugated. E, an intrinsic physical property of fundamental systems. F, Lorentz contraction at quantum level.
Heisenberg uncertainty is mostly used as relation between undefined position and momentum. We have two deltas in two conjugated values, and according to quantum mechanics, a minimum amount of uncertainty is inevitable. There is nothing special about these deltas. They represent a range of undefined values as everything else in quantum mechanics. In classical physics, we can have position with some uncertainty. In quantum mechanics, we have uncertainty of position without position. These factors are conjugated regardless of quantum mechanics, and they refer to a limit in knowledge. To sharply define the position of a system, you have to give up information about momentum and vice versa. Position is a coordinate value and momentum a physical relative quantity, but a system doesn't deal with its own position and velocity, while locality and momentum are conserved with respect to some relativity. So this uncertainty must be extrinsic, the consequence of an observation or interaction. Position is a dimensionless, abstract concept, so precision of position has no correspondence with reality. We can use the size of an electron at rest as one of the best meaning for precision of position. When we deal with massive objects, we can simplify them with the center of gravity, but energy of the Earth is spread over thousands of kilometers. I can find it here, but also here and here. Since the planet has an atmosphere, it is also really hard to find the smallest delta x possible. But in any case, my uncertainty doesn't affect the planet, and it has no consequences on its position. We now add velocity to the Earth, and an observer has frame of reference. Even when v is small, the huge mass of the planet results in an enormous momentum. The planet should also have an uncertainty of momentum with respect to the observer. Since delta x is very big, its conjugated delta p should be small, but at the same time, uncertainty of momentum is usually proportional to the momentum itself. In any case, uncertainties can change according to what I want to observe, but they do not affect position or momentum of the planet, because these delta are observer-related. The Earth keeps existing completely defined. Indeed, if I remove the observer, there are no more velocity, momentum, delta p and delta x. And as example, no matter my delta p, Earth's velocity is constant, otherwise we are violating momentum conservation. Anyway, Heisenberg uncertainty is not about knowledge of the observer, and instead should refer to something deeper. Looking at the fundamental level, systems have an uncertainty of relation that is at least equal to h over 4 pi, combining the two conjugated. Heisenberg uncertainty is not about independent systems uncertainties, but about the minimum intrinsic imprecision of conjugated when systems interact. This relates to statistical randomness of quantum mechanics. Each initial condition is capable of different interactions, so results have many combinations of uncertainty, but they are all equal to h over 4 pi. And here we are seeing how in quantum physics we have different outputs from the same input. This effect is anyway too small to be experimentally tested. And even if x and p are conjugated, at macroscopic scale, position uncertainty is not strictly bounded to momentum uncertainty. It is possible to identify similarities in our macroscopic world. Problem is to understand if the microscopic foundation exists. Heisenberg tries to show how his uncertainty emerged with the Compton scatter. Inside these interactions, Q is the uncertainty of position deriving from the wavelength, and P is the momentum uncertainty, is the scatter of the electron. Results in Compton are wavelength independent, and here we don't have to conjugate it. We have a cause effect with energy transfer. The higher the frequency, the higher the recoil of the electron by mere conservation. De Broglie can relate momentum of the electron to the wave, and putting them back together we have lambda h over lambda is about h. De Broglie shows how particles can behave as waves, but this doesn't transform waves into particles. Yet with such correspondence, wavelength can be used as momentum and delta p is made proportional to p. So the original concept, where the relation is extrinsic to each particle and intrinsic in the interaction, arbitrarily becomes intrinsic properties of single systems. Relativity is no more necessary, and velocity is now the constant c. Heisenberg paper talks about experiment with electrons, and here we found that the faster the particle, the more defined the position. This relation doesn't hold when we start dealing with massive systems as we saw with the planets. Heisenberg uncertainty lies in this size, a very tight relation between conjugated. We can find similar effects at macroscopic scale, but we can't reach this level to verify it's true. On the other hand, the position-momentum relation can be largely contradicted. I can have two big uncertainties, and the greater the mass, the worse it becomes. About the correlation between delta x and delta p, it is stated that for one growing the other shrinks, but above this we can easily break the relation because the only constraint is the lower fundamental limit. We don't know if Heisenberg's relation is correct, but we assume a discontinuous reality with huge implications. Spacetime is continuum until proved wrong, and opinions don't matter, so we can't admit this. In physics, the line separating negligible from non-existing has become very thin, so claiming quantum mechanics is meaningless at macroscopic scale is just another way to say quantum mechanics keeps being disproved by experimental results. For example, following this scientific method, in no way we can witness a teleport violating relativity. And if this effect doesn't make any difference, it doesn't exist. Otherwise, I can invent anything. The principle is underdefined and can be distorted. And since we now have intrinsic Heisenberg uncertainty, we can make it mechanics. Quantum mechanics can apply Heisenberg uncertainties in many ways, causing consequences. Since Heisenberg uncertainty is about undefined position and momentum, someone might naively think of stopping the system to make the uncertainty disappear. If the object is still, I have no doubts about its place and speed. Sadly, without velocity, Heisenberg uncertainty breaks down, and the lack of motion also makes position disappear, showing how good is this model. If indeed the system is stationary, quantum mechanics is unable to define its position and need the system to move. So to say, system has uncertain position because it moves. Luckily, the faster it goes, the smaller delta x. So shooting the Earth at 0.5 CE allows us to better define its position, because now it's moving at half of the speed of light, but delta x is just 11,000 kilometers. Uncertainty of position cannot affect the position or the actual size of the system. Going faster doesn't make the system more defined because it always has the same dimensions. What it can change is the dynamic of interaction. So again, Heisenberg uncertainty is not intrinsic to single systems. Since Heisenberg uncertainty won't work lacking velocity, there are two simple solutions for these cases. Don't use it, or apply it anyway, creating unjustified movement. Let's say a minimum combination of thrust and lift is necessary to fly If, for example, lift is very low, a greater thrust is needed to keep this valid. It can be higher, but it cannot be lower. And when I observe an aircraft, I can maybe find this relation, but it's not always true. On the other hand, in quantum mechanics, we can make even dolphins fly. All forms of energy in the universe are forced to a minimum amount of uncertainty by quantum mechanics. Applying the relation, every system is compelled to this value, ignoring whether this has any correspondence with physical reality. So we can assign the thrust lift ratio even to dolphins, making them fly because now this is at least equal to g. This relation can be correct, but thrust and lift must have a source. We cannot just apply the formula and magically fly everything. Also, since we don't need a cause, this minimum amount can last indefinitely, and the dolphin can fly forever. As with the dolphin, quantum physics also uses Heisenberg uncertainty as mechanics. Each system is affected by this principle, even when it's free and undisturbed. Quantum mechanics apply the Heisenberg uncertainty to energy systems and cause motion. Delta X becomes boundaries that put systems into motion. The smaller delta X, the greater the gain in momentum with its uncertainty. Sadly, the movement is forced and it's as unjustified as the boundaries. How can a space coordinate give additional momentum? This derives from the mathematical framework in place of reality. In fact, reality proved this wrong. It just doesn't happen. If boundaries are responsible for some dynamics on the system, something physical is occurring, and we are witnessing a classical action-reaction behavior. A system moving at 5 meters per second is placed into a box. The particle reacts to the boundaries and bounces back. Considering the interaction elastic, the system is conserving its momentum. Having the available space, we double the apparent frequency, the number of bounces, but the system is not going faster. On the other hand, if the particle is not moving, putting some boundaries have no consequences. Effects and interaction must have complete physical causality, and even more, boundaries must be justified. Nothing said until now changes that. If boundaries are present, they are consequence, not cause. The same is valid with waves. When quantum mechanics doesn't have an outcome, can fake it with an arbitrary potential. Waves are now contained and we are ignoring quantum rules, as example the collapse interacting with the barrier. The description works because we are using the Schrödinger's equation, while the effects caused by the boundaries becomes intrinsic properties of the wave. Similarly, we have cases where the uncertainty causes spread and contraction with waves. A small delta x causes delta p to shrink and delta x to grow, and dynamic reverses with small momentum uncertainties. Small and large are aleatory, they don't have proper meaning, and starting from a single wavelength, here with quantum mechanics we have totally defined momentum and maximal uncertainty of position. As comparison, in Compton, the smaller the wavelength, the better we define position, while here one frequency always means completely undefined position, because every wave, according to quantum field theory, has uniform probability over the entire universe. If we superpose more frequencies, we have an increasing smaller delta x and larger momentum uncertainty. This is an artificial construct, starting from the assumption we have infinite extension for single waves. Following Heisenberg, this smaller space uncertainty should cause the system to spread and bring it back to its initial condition. but it doesn't. As with the particle in a box, the wave packet conserves its state. And we already saw that superposition of waves have no consequences. Even in cases where a small system wants to expand, we can't ignore the work we put in to cause the instability and from which the system wants to move away. It would be a reaction to our action, so it's not spontaneous but a consequence. If this delta x is too small and the system wants to spread, it means that a physical cause originates this unstable condition. Otherwise, we talk about a system doing work on itself to unreasonably act against the minimum action to then following spread out. While the exact relation can be proved, this loose conjugated mechanic refers to a loop that can only hold with arbitrariness. Equally important, no matter what mathematical trick it's pulled from the head, we can't relate Heisenberg uncertainty to waves, since the principle refers to uncertainty in particles' interaction. Waves don't have that. Looking instead at massive systems, I can have two big uncertainties without consequences, and there is no direct correlation between how much space the system occupies, its position, and its momentum. It's only when I try to measure that, based on conditions and the interaction I choose, it is defined what and how sharply I can know about a system, but my uncertainty cannot affect what is real in the system. Reality of the system can change following my observation, but it's an action-reaction consequence that is proportional to the interference of my measurement. Heisenberg is also fundamental in making quantum field theory works. Combining uncertainty with oscillators, we can get literally infinite energy that is renormalized and then agree with the experimental results. And it is also dramatically used to create particles from nothing in colliders, trying to fit the standard model into reality. The universe can lend energy that doesn't exist. We just need to respect Heisenberg guideline, which here becomes the larger the energy depth, the shorter the term. Leveraging on this credit, quantum physics can do all kind of transformation for free before returning back the extra amount. Since the initial status and the outcome are facts respecting conservation of energy, agreement is all quantum mechanics needs. And the laundering in between is swept under the rug. None of the mechanics we saw have a reason to exist. Heisenberg uncertainty refers to the lower limit in interactions with particles. It is not about knowledge. It doesn't refer to independent systems, and it's not source of mechanics. Find the microscopic similarities don't support the fundamental uncertainty, and more important, we found a lot of contradictions. Nothing of what we saw proved the exact relation of conjugates true. Twisting Heisenberg, quantum physics transforms an extrinsic effect as a consequence of interaction to an intrinsic cause of mechanics. It can be done because it's quantum mechanics. We'll never see it in any case. In quantum mechanics, no property exists until measured and it disappears an instant later. This obviously is unphysical and against all conservation. Undetermined doesn't mean unexistent, or that the system is undefined within some deltas. It means unknown. If a system has a phase, such phase exists as a finite property, regardless of our ability to quantify or locate it. Heisenberg uncertainty survive because in quantum mechanics everything is ambiguous and statistics. It's a theory entirely running on invisible randomness. So it's like someone blind pretending reality is the messed up. This principle is impossible to perceive in our macroscopic world. And the quantum uncertainties, as all other quantum effects, are negated by the scientific method. We have no evidence of their existence. What is interesting within this framework is the uncertainty age. It relates to the fine structures and Planck's constants that we can measure and observe, but